Hi, everyone, and welcome back for part two of chapter 5 on short term and working memory. We're going to kick off part two with this sort of shift from the concept of short term memory into a more, I guess you could call, elaborated version of short term memory that we call working memory. So I'll set this up a little bit for you. Remember that short term memory was where we hold small to moderate amounts of information for a brief amount of time, maybe 15 to 20 seconds. It's sort of the things that you currently have, quote unquote, in mind, right? That's short term memory. In the 70s, Baddeley and Hitch basically said, short-term memory is fine. That's a good concept, and it's a legitimate concept, but it seems to be incomplete. And so they elaborated upon short-term memory into what they call the working memory system. So working memory, just like short-term memory, is a limited capacity system for the storage of information. But what they added is that this is also a place where the information is manipulated so that complex tasks like comprehension, learning, and reasoning can be completed. So what they added was not anything really about the fundamentals of short-term memory, which is it's a limited capacity temporary storage system. What they added is the idea that, okay, so you have this information on your workbench, and what's the purpose of a workbench? It's to work on it. It's to do something to it. So they elaborated on this idea of short-term memory by saying working memory really involves the sort of gymnastics of complex cognition in the conscious mind. So the manipulation of information for complex tasks. So again, short-term memory holds information for a brief amount of time. Working memory is the idea that, yes, you hold it for a brief amount of time, but really the purpose is to do stuff, right? It's to engage in processing and manipulation of that information. So if I asked you, what is 43 times 4? The sort of traditional way to solve this math problem would be to say, okay, 3 times 4 is 12. Now I'm going to hold the number 12 in my head, right, in my mind. Then I'm going to do 4 times 40, which is 160. Then I hold 160 in mind. And then I pull them both back together and I say 160 plus 12 is 172. Right? I have visualized 43 times 4. I've held 12 in memory. I've held 160 in memory. And then I've added them together, right? I've done something with that information. And that's really the crux of working memory. Not only am I just storing information, I'm working with that information. And so just think about working memory not as a completely different system. It's just an elaboration or a clarification on the idea of short-term memory. Now, of course, nothing would be complete without a little bit more complexity. Working memory is shown to have a couple major components. The first thing we need to consider is the central executive. This is a control process that governs the functioning of working memory. And then working memory has two other major components. The first is the phonological loop, which is the working memory storage place for verbal and auditory information. So words, speech, internal speech, external speech, anything that's verbal or auditory is stored in the phonological loop. Anything that's visual or spatial is stored in the visuospatial sketchpad. And then the job of the central executive is to do that work. So think about each of these, the phonological loop and the VSSP, as their own sort of miniature workbench. And then the central executive is the worker. It's the person that comes along and moderates the doing. It moderates the work. It's the executive control function of working memory. So think about, and I'm going to maybe stretch the analogy a bit here. Think about this white square as the workbench. And then on that workbench, you have two buckets. You have a bucket for verbal and auditory information, and you have a bucket for visual and spatial information, and they're separate buckets, right? You can fill up the visual bucket, and it doesn't impact the phonological bucket, and vice versa. And then you, quote unquote, are the central executive that controls what you're doing and what you're using. Do you need to grab things out of the VSSP bucket? Do you need to grab things out of the phonological loop bucket? Do you need to put them on the main table and combine them? So on and so forth. The central executive is the worker. The phonological loop and the visual spatial sketchpad are the buckets on the workbench. But notice that the central executive can probably only handle so much information at one time. It can't infinitely deal with all possible amounts of information. It has limitations. So while the ability to fill up each of these buckets is independent of one another, perhaps the ability to combine and work between these buckets is not unlimited. It does have some limitations. So we can sort of expand out our full memory model to look something like this. We have input to sensory memory. Most of the things in sensory memory decay quickly. The things that you add attention to move to the central executive. The central executive partitions out data and information to the VSSP, the visual spatial area, and the phonological loop. The phonological loop has the store and articulatory control, which we're going to talk about here in a minute. This is really a sub-process. So the central executive manages the distribution of information to those two things, and information moves back and forth. Then the central executive decides, or is the sort of worker that allows the movement of data and information into and out of long-term memory. So the central executive is our worker, and everything else is kind of a storage space. All these boxes are storage spaces. The central executive is a worker, and these arrows are processes. I know it's a lot. I know it's a little confusing, but this is, given the last 100 to 150 years of memory research, this is our best guess as to what's going on in your memory systems. Okay. So working memory is actually set up, as we could probably intuit from these separate structures. It's set up to process different types of information simultaneously. We can process auditory information at the same time that we process visual information. Just think about the way that you move about the world. You can see things and react to them, as well as hear things and react to them at the same time. You have trouble when multiple inputs of information are similar. So if you are trying to read a book, music or someone yelling, so other auditory information, is more disruptive than if you were disrupted by visual stimulation. So when information is of similar type, so visual or auditory, then you have trouble because they disrupt each other. But if information is of a different type from one another, so visual versus auditory, you can process them together more easily because one piece of information is going up here to the VSSP, and the other piece of information is going down here to the phonological loop. So you can handle information at the same time as long as that information is different types of information. What is more difficult to handle is multiple inputs of the same type of information. So let's talk about the phonological loop. This is where we store and then rehearse auditory information. This rehearsal or repetition of information is what helps encode it into long-term memory. So the phonological loop or phonological store is a holding space. And then you have this process called articulatory rehearsal, which is where you internally or subvocally, so that means without vocalizing, you subvocally rehearse information. This is the repeating a phone number to yourself in your own head so that you can try and remember it. So we have the storehouse, and then we have the rehearsal process. Those make up the phonological loop. And we know that this is the case because of many, but we'll highlight two interesting effects with auditory information. The first is the phonological similarity effect. Basically, letters or words that sound similar are more easily confused with one another. Additionally, we have the word length effect, where even if the number of words in a list is identical, the list that has longer words is more difficult to remember, presumably because the longer words take more time for rehearsal. And we'll see an example of this in a minute. Okay, so a simple experiment on the confusion of letters or words that sound similar, the phonological similarity effect. Conrad, 1964, conducted a letter memory experiment, super basic. You basically just present individuals visually with letters and tell them to remember them. What Conrad noticed is that when participants made errors, they often misremembered with similar sounding letters. So for example, if the letter that you were supposed to remember is F, you are more likely to misremember it as S or X. Notice the F, the sound here. F, S, X, right? These three letters have very similar sounds, even though they don't look really anything like each other. So the confusion was not based on the visuals of the letters. The misremembering or confusion was based on the way they sound, which suggests a memory process based on sound, not based on vision. And here we have the word length effect. On the left, we have 1, 2, 3, 4, 5, 6, 7, 8 words in a list. On the right, we have another 8-word list. So if memory for auditory information, so words, if memory for words only is dependent upon the number of words, then these two lists should have equivalent memory abilities, right? If I get 5 in list 1, I should be able to get 5 in list 2, because it's just based on the number of words. But let's think about what you would be doing if I got you to try and remember list 1. So I present to you list 1, and what do you do in your mind? You go Beast, bronze, wife, golf, in, limp, dirt, star. Beast, bronze, wife, golf, in, limp, dirt, star. Right? You use that subvocal rehearsal mechanism to repeat them and try and remember. And you would do the same thing for list 2. Alcohol, property, amplifier, officer, gallery, mosquito, orchestra, bricklayer. The difference is that list 2 takes much longer to rehearse because the words are longer. They have more syllables. And so what we find is that for a list like list 1, people can remember 77% of the words. But for list 2, people can only remember 60% of the words. Again, what this suggests is that there is a auditory memory system that is dependent upon time. Remember, we're still talking about short-term memory. It only lasts for so long. And so because this auditory rehearsal and memory mechanism is dependent upon time, you can fit more words into it if the words are shorter because the words take less time to rehearse. And you can fit fewer words into it if the words are longer because they take more time to rehearse. I just answered that question. Okay. We also, a third line of evidence for the existence of the phonological loop is articulatory suppression. Basically, if someone is trying to do an auditory memory task, if you talk over them, if you make them listen to something else, if you make them repeat other words or numbers or letters, it suppresses their ability to rehearse the original information. We've already seen this, if you remember from part 1, the experiment where participants were given 3 letters and then they had to count backwards by 3s. That's articulatory suppression. The counting backwards by 3s suppresses your ability to rehearse the 3 target letters. And if you're not rehearsing the 3 target letters, you lose them, you forget them. And this is evidence for a rehearsal space, a phonological space. Phono meaning sound, right? That's where we actually get the word phone. So a sound space where you rehearse this information. And we see evidence of this in real life, just using digit span in college students who are either practicing their digits to remember in silence versus doing karaoke versus speaking versus doing karaoke, listening to speech, and then speaking themselves. They are being vocal. So many college students think that they can study or write while they listen to music. And this evidence suggests that you're better off in silence because your phonological memory abilities are better in silence than they are when you're engaged in another auditory task. An alternative often given and mentioned, which I think makes some sense, is that if you would like to listen to some kind of music, listen to nonverbal music. So listen to classical music, listen to electronic music or EDM, something like that, that has the sort of rhythmic tone to it, and it's auditory, but it's not verbal. Right? It is probably the better way to go than trying to read and study or write while listening to music with words. So I think it's always a great opportunity when we talk about the phonological loop and memory abilities to take a step back and ask some really interesting questions like, what about people who are deaf? Because if we're proposing this system that's based on audition or hearing and speaking as being sort of fundamental to human memory systems, then what happens if someone can't hear or speak? Do they develop completely different memory systems? That would be a little problematic for our theory, because it would mean that these memory systems are not sort of inherent or innate to people. But don't worry, the data suggest that even the deaf have a system that functions like the phonological loop, except in the signing deaf population. So deaf individuals who use ASL, for example, in this experiment, American Sign Language, we see similar effects based on the length of time it takes to make a sign with their body. So some signs are very small movements and very quick movements, maybe just with fingers or hands. And then other signs are much larger. They might involve the head, the face, movement of arms, of the entire upper body. And so we find that memory for signs is more difficult when the signs are big signs. They take more time, they take more movement and effort. And memory is better for small signs because they can be rehearsed more quickly. And we see a sign similarity effect, just like the phonological similarity effect, where deaf signers are more likely to confuse signs that are physically similar to one another than signs that are different from one another. So what seems to be happening is that individuals who are deaf basically take this phonological loop, this system that's meant to be an auditory system, and their brain shifts it to be more physically based, but it maintains the same basic properties of the phonological loop. And this is good evidence that the phonological loop is a real thing. And it's also good evidence for what we call brain plasticity, or your brain's ability to shift and change as needed. Here's the data on that. Sorry, I jumped the gun with the explanation probably, but here are the data. Basically, levels of memory ability are sort of mimic and are similar to the verbal or auditory memory abilities we see in non-signers. Okay, so that's the phonological loop. What about the visuospatial sketchpad, which is the proposed place where we store visual and spatial information? In 1971, a really groundbreaking experiment was conducted called mental rotation, which asked people a very simple question. It showed them two geographic figures. So let's take these top two figures. And it asked participants the question, are these figures the same or are they different? To answer that question, you have to engage in mental rotation. You have to, for example, take the one on the left and you have to sort of twist it in your mind and see if it fits with the one on the right. In this case, it does, right? These are the same figure. We're just seeing them at different angles. Now, when you do that, when you hold it in your mind's eye and rotate it, you are using the visuospatial sketchpad. That's where this is happening. And we can see a second example on the bottom here. Are these the same figure? You have to sort of rotate and rotate. And I believe these are also the same, right? If we sort of rotated this one back and this over here. Yep, these are the same as well. Okay, cool. So we have the place where the visuospatial sketchpad exists. The interesting thing is that the further apart the angle between these two figures, the longer it takes you to answer. And this is basically a perfect linear relationship, which is pretty astounding. Meaning that the angular difference between these two is, let me rephrase that. So here, the top two figures, the angular difference is relatively small, right? It's pretty quick to rotate the one on the left to fit the one on the right. And so you're fast at answering it. The y-axis here is time, the x-axis is angular difference. Versus B, the one on the bottom, the angular difference is greater, and thus it takes you longer to answer. So this is really good evidence for this space where we hold and process visual spatial information. Now, as I mentioned before, we have this sort of amorphous thing called the central executive, which is the control mechanism. It's the controller. It helps you focus, combine, divide, split apart, switch attention back and forth from all of these different pieces of information. And maybe most importantly, it helps suppress irrelevant information, meaning it helps you ignore things that need to be ignored. Now, when your central executive isn't working properly, you end up with errors of perseveration, or basically repeating the same action even though it is not achieving the desired goal. This is common in individuals with frontal lobe brain damage or frontal lobe developmental disorders. And it's also common in people who have voluntarily inhibited their frontal lobes through the ingestion of drugs like alcohol. So one of the things that alcohol does is it stops you from suppressing irrelevant information, and it also stops you from inhibition, right? That's really kind of the flip side of the same coin. What do you do? How do you behave when you've been drinking alcohol? You are less inhibited. You're more likely to dance. You're more likely to go ask that person, for their phone number that you think is cute. But you're also more likely to get angry, to get mad, to fight, to say things that you don't mean, or that you do mean, but you should be suppressing. Alcohol is basically compromising your frontal lobe and your central executive. Now, to complicate things just once more, in really the last decade or so, Baddeley, who's the psychologist that came up with this working memory model, has suggested that there needs to be one more additional piece called the episodic buffer, which is, we'll look at this diagram, which is almost like a spillover storage space for when maybe the phonological loop and the visual spatial sketchpad are too full. You can start to fill up the episodic buffer. Even Baddeley basically says, this is kind of ill-defined. We're still trying to figure out what it is. But evidence suggests that people are better at these processes than they, quote unquote, should be, given the limitations we know of the VSSP and the phonological loop. And so this led Baddeley to sort of theorizing about this tertiary, this third structure within working memory that's basically a spillover place, because we seem to have better working memory than we should. And so maybe there's this other thing out there that we haven't quite figured out yet that's like this little added, extra memory capacity. It'd be like you buy a new iPhone and you bought the 32 gig, but it turns out you're actually working with 64 gigs of memory, right? So the phonological loop and the VSSP should add up to 32, and that should be all that you get. But your phone actually ends up with 64 gigs. And so you're like, what the hell's going on? Turns out there's a little extra memory in there. That's kind of the analogy for the episodic buffer. There's this extra memory that we seem to have that's kind of ill-explained right now. We don't really know what's going on, but we can theorize about its existence because we seem to be better at these abilities than we should be. We paid for the 32 gig, but it turns out for some reason we have a 64 gig. So let's talk about the brain just a little bit with the last 5 or 6 slides or so. The prefrontal cortex, so that's the foremost part of your brain, so basically your forehead right behind your eyes, is the area of the brain that's responsible for this sort of working memory, central executive processing of visual and auditory information, as well as the combination of that information, as well as the inhibition of unnecessary information. And we know this because people with damage to their prefrontal cortex have difficulty with these processes, as well as, and we can, in the past, we've done these experiments with monkeys, right? Monkeys with damaged prefrontal cortices have difficulty doing things that involve working memory. And furthermore, working memory seems to be tied to specific neurons. So I want you to imagine a primate that is looking at this screen on the left, and they get a cue, right? They get this blue box, and the presence of that blue box activates some neuronal activity. Then the square turns off, and that same neuron continues to fire until the monkey shows that it remembers where the square was by moving its eyes to that location. So in this task, obviously the monkey can't tell you that it knows where the box is. What they've done is they've trained these monkeys to move their eyes to where they remember the box being. And what's interesting is that there's some activation when they move their eyes, but there's actually more neural activation in sort of the interim in between period when the box is gone, but they're waiting to move their eyes. So this initial activation to the presence of the box is maintained in the interim. And it's thought that this maintenance of neuronal activity is working memory, right? It's the maintaining the rehearsal of that information, in this case, in the visuospatial sketchpad. So we actually have single cell neuronal recording evidence for the maintaining of that information in mind. And it's thought that this activity reflects the functioning of the working memory system, specifically here, the VSSP. That's what I just said. And slightly more complex way of thinking about how this works in the brain is a neural network perspective. So this is a single cell perspective versus in 2015, Stokes did some work to hypothesize about how maybe neurons work together to produce memory and working memory. And he proposed a couple different states of being called the activity silent working memory system. So first, there's an activity state where incoming information that we want to remember causes neurons to fire, right? Boom. Incoming information causes neurons to fire. And then you have the synaptic state, where once those neurons have stopped firing, they strengthen their connections with each other. So it looks something like this. We get input, individual neurons fire, that's the blue. When they stop firing, then the arrows between them, right, sort of the synapses, the connections between these neurons start to strengthen, such that what ends up happening is that a memory is not the activity of a single neuron, but a memory, or the act of remembering, is tied to the synchronous activity of multiple neurons all working together in their associated connections. So when you form a memory, what you're doing is changing the physical structure of your brain. You're creating new connections. You're strengthening existing connections. And then when you remember, you are activating that neural connectivity system. You are, and again, strengthening the association between those neurons. So we can think about these things occurring at the individual neuron level, and then we can sort of add a layer on top of that to this neural network level. And lastly, just really quickly, people vary in their working memory capabilities and their capacities. So there's just natural variation. Some people are really good at working memory and have a high capacity. Some people have lower capacity working memory. And when we measure their brain activity during a task, we find that one of the things that critically separates the high and low capacity individuals is that high capacity participants are more efficient at ignoring distractors. High capacity participants are more efficient at ignoring distractors. And so the research here basically ask people to remember sequences of target rectangles, and then added distractors to those sequences. And the people that are good at the task are good because they can ignore the distractors better than people who are poor at the task. So that's it for working memory. Thanks for listening. And we will pick up with Chapter 6, which is on the structure of long-term memory. So thanks, everybody, and I will talk to you later.